Our next application for multi-objective least squares is estimation and inversion. I mean, it's a huge field. I'll say a little bit about it. You could take entire courses on nothing but this, but we'll say a little bit about it now. So your model is this. You have a so-called measurement model. And here you have an n vector x, and that's the parameters that you want to estimate. That's what you want to estimate. And you don't have a way to directly measure them. Okay, so could be that x is going to be the density of voxels under the ground. You don't want to drill a test well to actually measure it. Okay, y is going to be a vector of measurements that we take, right? So these could be measurements that we take above ground, for example. Then what we're going to do is we're going to say that the model looks like this. It's y equals ax plus v. V is the vector, right? So sorry, it's a vector of noise. Let's see, or disturbances or errors or however you want to think of it. So here, y equals ax is a linear model. Now, a comes from either physics, first principles, all sorts of stuff, right? But a represents the mapping from the parameters you are interested in measuring or estimating, and how they map into the things that you actually really measured. That's why. And v is sometimes called the measurement error, something like that. Okay. All right. So that's the idea. And in estimation you would know a, that describes your system, and you would observe y, and your goal is to guess x. Okay. Now, one interesting thing here is if you know y, and you know if you know y, you know a. If you make any guess x, you can look at y equals ax, and you're basically guessing what v is at that point, right? So v is y minus ax, and in basic least squares estimation, it goes like this. We will simply assume that this noise vector is small. So that's what it means. It's like I took these measurements. I took 250 measurements of temperature. Yeah, they're all, I don't think any of these temperature measurements is exactly correct, but they're all probably within, 0.1 degrees C or something like that. So this kind of fits the idea that the measurements are good, but they're not perfect by any means. Okay, and so here's least squares estimation. You are going to guess x by minimizing norm ax minus y. Now let's note what that is. Ax is what our model says y would be without noise. Y is what we actually observed. And so this says, please choose me an x for which our model output would match as closely as possible what we actually measured. So that's least squares estimation. And it's completely normal and makes perfect sense. I should also add that this vector is minus v. So another way to say it is, please choose an x so that, given the noise we observed, that tells you what v is, and that's the measurement noise. And you say, please give me an x for which we have to imagine that the measurement noise is very small, as small as possible. So that's least squares estimation. Okay. Now, sometimes when people do this, in fact, very frequently when people do this, they had regularization. And that's called either regularized estimation, sometimes called regularized inversion, something like that. And the way that works is you simply factor in to the problem you solve to guess x prior information about x. And that prior could be things like this. You think, well, I don't think x should be too large. That's what I think. Or I think x should be smooth, something like that. So, and you can have all sorts of priors here, right? Now, in other courses, you would study priors like, I think x has to be non-negative, or the entries of x are between 0 and 1. We can't handle that in this course, but you'll see other courses where priors like that can actually be handled, but not in this course. And nevertheless, what we're going to talk about here is good enough for many, many applications. So let's see. Now these are expressed. The prior information about x is expressed using things like norm x squared. That mathematically expresses the prior that x is small. And that's got a name. It's called Tikhonov regularization. And that's based on, this is named for a Russian mathematician Tikhonov. Another one would be J2 equals dx, where d is some kind of difference operator. For example, if x is a time series that you're trying to guess, but it can, well, if it's a time series you're trying to guess, dx is the matrix, the difference matrix, and so dx is the differences, and it says you would like to guess an x which is smoothly varying, and that would be this use. You'd use J2 here. Then you'll minimize J1 plus lambda J2. And then there's the question of what value of lambda do you choose. And so I'll be honest, in many applications, it's just done, it's ad hoc, and you adjust lambda until you like the results. I mean, visually it makes sense. Or you go find an expert in the field and you'd say, hey, I'm estimating this. Does this look cool? Is this kind of what you'd expect to see? And when the expert says yes, then that means you've got lambda right. So, okay. Now, the x hat, the one that minimizes J1 plus lambda J2, that's a function of lambda. And so we're going to denote that as x hat of lambda. And that's called the regularization path. It's like a curve where you change the parameter lambda, and this point in our n, in this n vector, moves around along a curve. And that's called the regularization path or curve. Now, there's some very interesting things happen when you look at this. When you minimize this in Tikhonov regularization, for example, you end up with A getting stacked on top of a multiple square root lambda, actually, times I, the identity. And the result is that even when A has dependent columns, the Tikhonov regularized inversion least squares problem is well, it makes sense, right? It's got independent columns. So it's very interesting. So it means you can actually do quote inversion even when you have fewer measurements than you have parameters you want to estimate. That happens when A is wide here. That's called a wide system. Okay, so we'll look at a specific example now. It's very simple, and you can see there are a lot of other examples, but we'll look at this one. So here, X is representing an image. So that means it's in some order. It's the voxels, and it's a monochrome image, grayscale. So in some order, maybe I go across the rows and I list those. But so X is an image, and it's probably not small. It's maybe like I don't know, at least 10,000 or maybe 100,000 million, 10 million high. Okay, then the matrix A is a blurring operator. And we've seen that. It could be like a convolution. That's a very simple model of how some, for example, optical systems work, is that you convolve what you really see in the image plane to get what you actually observe or measure in your microscope or camera. Okay, so then you can think of y equals ax plus v as a blurred, noisy image. We'll see examples of it pretty soon. Least squares deblurring says this. It says, I'm going to give you y. That's the blurred image. And it says, I'm going to choose an image, x, that this first term says ax is actually what the image would be if there were no noise. And so you say the first thing I want to choose x so that what the image would be without noise is at least close to what I actually observed. So that's the first term. The second term is regularization. It's the Dirichlet energy. Dirichlet energy is, in this case, for the case of an image, it's actually a sum of two norm squareds. And these are gigantic matrices, super sparse, by the way, dv and dh for vertical and horizontal. And these give you the horizontal and vertical differences for an image. And so these are, this is really big. But the idea is we can solve it. It's also super sparse, by the way. And here, what this says is, please get me an X that under my image blurring model would have produced what I saw. Close enough, or close. But also, I want X to be smooth. Why? Because I might know ahead of time X is smooth. Okay, so that's what this would be. And then we would turn lambda and until we like what we see. That's one option. Is you do this and you turn lambda until you look at the output and say I like it, I don't like it, something like that. There are more principled ways to choose lambda. For example, you could have some experimental setup where you know the image exactly. You actually know what x is, and then you could judge you could choose lambda by trying under these careful experiments, doing this and seeing how close x is to the true x. So that would actually be a very reasonable way to choose lambda. So we'll do an example. It's a footprint on the moon. So here is on the left, you see the blurry, noisy image. So that's the blurry, noisy image. And here's what it looks like. And I chose lambda equals 0.007 because, I don't know, to my eye, it looked the best. But, again, you could do this many, many other ways. And actually, if you look closely at them, you'll see it actually did something. It actually sharpened up the edges pretty well. I mean, it's actually like you can see visible deblurring. Oh, and this would be called, you might call this least squares deblurring. Deblurring means to undo the effects of this blur in some optical system. Okay. Now, I'll show you the regularization path, or I should say, I'll show you like 4 points on it. So if I take lambda equals 10 to the minus 6, that basically says, if you go back to the problem here, it basically says, don't worry about this term. And it says, just get me something that through my forward model, I should say sometimes this is called the forward model, would produce the image I actually saw. And this says, the fact that lambda is 10 to the minus 6 says, you know what, don't worry about x being smooth too much. And sure enough, look at this. It's not smooth at all. Actually, the good news is it's pretty sharp. Bad news is it's not smooth at all, okay? Here is lambda equals 10 to the minus 4, and you can see by cranking up the parameter that scales the regularization, which is the smoothness, you can see it's still pretty sharp, but it's getting smoother. So again, that makes sense. I should point out that the lambdas are varying over a very wide range. This is very common in multi-objective least squares. It's very common that the lambdas, that the weights vary over a wide range, and it's usually logarithmically spaced. People have found that simply just works better. Okay, here you go. This is increasing lambda. This is 10 to the minus 2. And the good news is you don't see any more of that little speckle stuff anymore. But it's still actually I would have to say it is definitely better than the original blurred image. So you're still getting some blurring, some deblurring at 10 to the minus 2. Okay, and then here it is with lambda equals 1. And now you can see what's happened now is I'm putting too much emphasis on the reconstructed image being smooth. And so it's kind of I'm losing some of the details of the edges and things like that. And so that would give you this thing here. And if I went to lambda equals 100, what do you imagine it would look like? Well, I can tell you. If you go to lambda equals 100, I don't have it here, but if you go to lambda equals 100, it would just be like a kind of a gray-white blob. It'd be so smooth that you might not even be able to detect it as a footprint. So, okay. Another example of this, a very, very common widespread is tomography. So the idea in tomography is that x represents the values of some quantity in some region of interest. And these are called voxels if it's in 3 dimensions and pixels if it's in 2, right? So I'll show you an example. Here's some region here, and I have set it up as an array of 5 by 5 pixels because this is in 2 dimensions. So we call these pixels. And the idea is I'm going to approximate the value of something as sort of constant in each of these boxes, right? By the way, people would not do this with 5 by 5. I mean, they would be more like 100 by 100 or 1,000 by 1,000 or something like that. But this is just to illustrate how it works. And then to give x as a vector, I might, for example, do the row. I'd give you the first row, second, and so on. So this would be x25. So if I give you a 25 vector, then that corresponds to a set of a bunch of values in this region. Okay. Now, in tomography, the basic idea is that you can't go in and measure stuff. maybe you can, but you don't want to because that's invasive. Um, but what you do have is you have integrals along lines through the region. So that's the typical thing. And so here's a line that goes through this region, and what it is what I get here is precisely this. I get the length of that line times the value of this x. That's x. That's probably 11, and so that is probably 16. X16 if I did my index arithmetic correctly. That's x17, and you can see that it takes that's the coefficient. So it's the length of the line here. So you can see actually that each row, we're going to write that this way, that yi is it's sum I equals 1 to n aij xj. Aij is the length of the intersection of the line and measurement with voxel j. So that's the picture here. You can see that this is actually kind of sparse. Like, so for example, in this particular example, that line goes through 1, 2, 3, 4, 5, 6, 7. It goes through 7 of our pixels. We have 25 pixels. So that means that 18 entries of the row of A corresponding to this measurement are 0. So this is very typical in tomography, is that sometimes it's things are the so-called measurement matrix, that's what A is sparse. Okay, now the goal here is to do the following, is given a bunch of values of y, and these are measures of these line integrals, the goal is to guess x, right? And so, classic example would be, a CAT scan or something where I would send X-rays through, and an X-ray just shoots right through, and if you transform the actual variables like the log of the intensity correctly, then what you'll find out is that this model is pretty accurate, right? If it's a little tiny beam, but it looks something like that. And the idea is from seeing the integral along different lines, we could actually kind of guess what x is, right? So, okay. So least squares tomographic reconstruction goes like this. The primary objective is something like that. A is our measurement model. It tells us specifically how x would map to y, right? And so x is the values at the pixels or voxels, and y is the observed line integrals through the medium. Now we add to this regularization, and they would capture prior information about x. For example, it could be that x is small, or it could be that it's smooth, in which case we'd use the Dirichlet energy, and we might even do that this way. But we might use we would minimize then ax minus y squared. That's our primary objective. Our secondary objective, in fact, we could have 2. We could make it 3. We could have this something like this. Might look like that. Sorry. That's what I meant to do. Whoop, these are not subscripts or superscripts. There, okay. And here, omega and lambda are positive, and they are parameters, or some people would call them hyperparameters, that you tune to make this work well. Now, when you make lambda big, x is going to be small. If you make omega big, x is going to be smooth, for example. And if you make both small, you're going to fit what you actually observed, your actual line integral measurements well. So that's kind of the picture. So we'll do an example. Here's an example, and it'll give you a rough idea of what this does. Okay, so we have 4,000 line integrals that we're going to take. And the way we're going to do it is there are a whole bunch of points. We have 100 points here, so they're spaced at maybe 3.6 degrees apart from each other. So we have those points, and then from each point we spray out 40 lines equally spaced in angle. Okay, so this is just showing you maybe 80 of the different line integrals, right? So these are just lines that pass through our object. Now our region of interest is this square in the middle here. Okay, so I get a lot of integrals. Well, I get 4,000 line integrals, right? And we could say, I mean, some of this is kind of obvious, right? That if a line integral turns out to be small, it means it didn't go through very much. The x values it passed through were pretty small. If it's large, it means it had to pass through some part where there was actually like a high value. And so okay, so then what we're going to do is we're going to take this region of interest, this square, make it 100 by 100 pixels, so we have 10,000 pixels here, and then we're going to put this image, or not this thing, this object, and into this tomographic system, right? So it's actually kind of interesting. I mean, remember, you know, you're getting 4,000 numbers, and your job is to basically figure out what is in that box just by looking at the integrals that go through it. Yeah. By the way, no human being can do that. I mean, that's kind of obvious, right? But I mean, like, how do you do that, right? Well, good news is now you know. We'll just use regularized least squares reconstruction. And so for this example, if you have lambda equals 10 to the minus 2, that's the image you get, right? Actually, all I'm doing here is I'm taking x hat, which is this regularized least squares tomographic reconstruction. I take that and I rearrange it into a 100 by 100 thing and plot it as an image. So that's all these things are. And so I get something like that. Actually, I mean, it's just kind of cool to see you can do this. I mean, this is like, you know, and now you know what's involved. You stack a couple of matrices, QR factorization, done. 4 lines of code or whatever, right? So honestly, your plotting code is going to be longer for something like this. So now, you know, real tomographic reconstruction uses slightly fancier methods, but in principle, this is kind of what they do. I mean, this is what they do. So, okay, here's lambda equals 10 to the minus 1, and you can see what that means is it's slightly smoother. If you look, you don't see this kind of speckle is getting better. Here's lambda equals 1, 5, 10, and 100. Now, I think we would agree on a couple things. First of all, I think that's too little. Regularization, because this is all that little speckle. Here, the image is getting too smoothed out, so that's probably too much. Where you would go in the middle, I don't really know. Maybe 5, maybe 1. I mean, truth is, your best bet in this case would be to figure out what the application is. Like, for example, you might be working with radiologists, and then you'd ask the radiologist, which would you like? And they might, I don't know, they might even prefer this. And you'd say why, and maybe they wouldn't know, or they would say something like, oh no, it's exact, you know, this one has smoothed out some of those little dots, and some of those little dots are really important. And I don't know, that's the basic idea. So, okay, so this is least squares, or I should say regularized least squares, used for tomographic reconstruction. And this, the idea of tomography comes up in lots and lots of other areas. I mean, a very interesting one is I have a colleague who worked on tomographic reconstruction of the transit times on a subway system, which is kind of cool. So what they had was they don't know how long it takes to go from this stop to this stop on a subway, but what they do have is they have the sort of like the analog of line integrals, because what they know is a passenger went into this subway, this station, they took this train, transferred, then took this train, then transferred, took that train, and they know when they clocked out at the other end. So they actually know the sum of 3. And if you think carefully, that's kind of like a line integral. It's the sum of 3 things. And so basically, you have to extract from various sums the individual values, and that's the essential idea of tomography.